Hey Chemistry, Mrs. KJ here, 4.01 Conservation of Energy. Dynamite releases vast amount of heat and light energy when it explodes. Alfred Nobel invented dynamite in 1866. The explosion of dynamite forcefully demonstrates the vast potential energy contained in chemical bonds of unexploded dynamite. Besides releasing energy, chemical reactions can also absorb energy to form chemical bonds. The changes in energy during chemical reactions are an important part of chemical thermodynamics. Here you will learn about such changes in energy and how the total energy of chemical reactions is conserved. So chemical reactions involve energy. When it's released, it's called exothermic. When energy is absorbed, it's called endothermic. Chemical reactions involve mass, which is conserved. Goals for the lesson: identify chemical potential energy as the energy stored in chemical bonds of a substance. Contrast exothermic with endothermic processes. Give an example of an exothermic reaction. Give an example of an endothermic reaction. State the law of conservation of energy. And on slide 2, you can download the study guide. And from the study guide, I just left the first paragraph, the goals, and our keywords. Endothermic, which means that energy is absorbed. And of course, exothermic. If you look at the word part exo means out or released, like an exit or an exoskeleton. Dynamite explosively demonstrates energy released during chemical reactions. In the early 19th century, chemists recognized that unstable nitroglycerin could be used as an explosive. Mixtures of gunpowder and nitroglycerin were used, but they were too dangerous to handle because nitroglycerin was so unstable. This hindered the use of this explosive both in mining and in warfare. However, in 1866, Swedish chemist Alfred Nobel found that if nitroglycerin was mixed with diatomaceous earth or sawdust, it could be handled and shaped safely. Nobel's invention of dynamite in 1867 immediately replaced gunpowder as the explosive of choice. Although Nobel became rich from an invention that is sometimes used in warfare, he was a peaceful man. He set aside money in his will to establish the Nobel Prizes in science, peace, and literature upon his death. Where does the energy of dynamite come from? The chemical bonds between the atoms of the nitroglycerin molecule are not still. They constantly move. They bend, stretch, and rotate. These bonds have potential energy. When nitroglycerin bonds break, energy is released. Enormous amounts of energy in the form of heat and light in the following reaction. So we have our nitroglycerin as a liquid, yields, we have some nitrogen gas, some carbon dioxide gas, some water, and some oxygen gas. And here's the molecular structure of nitroglycerin. Exothermic reactions release energy, while endothermic reactions absorb energy. When a chemical reaction releases energy, the energy is usually in the form of heat. This type of reaction is called an exothermic reaction. A common way to measure the release of heat is as an increase in the temperature of the surrounding. When a chemical reaction absorbs energy, the energy is usually in the form of heat. This type of reaction is called an endothermic reaction. A common way to measure the absorption of heat is as a decrease in the temperature of the surroundings. So I added to our notes decrease in temperature under endothermic and increase in temperature as heat is given off when the chemical bonds are broken under exothermic. Exothermic reactions release energy. Watch the video to see an exothermic reaction between two chemicals through a thermal imager. So just a reminder that energy can be in many forms, and usually when we talk about endo and exothermic, we talk about heat being given off, but of course, as they mentioned, there's also light and sound and even electricity that can be given off as well. So it's not always really obvious. And that's why you can use the thermal imaging camera. So if it's hot, it's white, and you can see when it's mixing that, oh yeah, there's definitely heat. So of course you could also just use a thermometer. And you can see how there's a dramatic increase in heat. And therefore, of course, an exothermic reaction. All right, endothermic reactions absorb energy. So not all reactions are going to give off energy, so not all reactions are endo or exothermic, but some are. So as they're mixing it, you can see that it's starting to turn blue, which means it's getting colder because it's taking the energy from the air. So it takes it from the air, it also takes it from the beaker and from the chemicals itself. So that's what causes everything to cool down because it's taking the energy from what's around it. Next we have combustion. Combustion releases energy, while melting absorbs energy. Consider a burning match. The combustion of the match releases energy in the form of heat and light as the wood burns. Because the chemical reaction releases heat energy, we call it an exothermic reaction. Some other chemical reactions are endothermic. By contrast, consider melting ice. Okay, so we're switching from combustion, a chemical reaction, to melting ice, which is a phase change, which is a physical reaction. Because it was water before, it's water after. Combustion is chemical because it started out as wood and it turns into ash and other gases. So it changes to a different substance. Okay, so by contrast, consider melting ice. The solid ice absorbs heat energy to become liquid water. What type of reaction is this and why? And as we just said, because this change absorbs energy, we call it endothermic reaction. Other changes of state are exothermic, such as when liquid changes to a solid. So basically they're saying that chemical and physical reactions can be exo or endothermic. And there's kind of an easier way to remember which ones the phase changes are. And that's by looking at a phase change diagram. So if we notice, we have temperature on the y-axis, we have heat energy on the x-axis. So you have a solid, such as ice, and it's going to melt. Okay? When it's melting, the heat energy has to increase. Why? So that the molecules can spread out and so that they have more energy. Therefore, when something is a liquid, as you already knew, it's going to move faster than when it's a solid because it has more energy. Okay, so these molecules are moving faster. So they had to take in energy so that they have more energy to move around. That's why it's endothermic. So when it goes to liquid to gas, they're taking in energy so that they can move faster. When the gas gets rid of energy, it slows down and becomes liquid. Getting rid of energy is exothermic. When the liquid molecules get rid of energy to be slower and become solid, it's freezing, and again, it is exothermic. Chemical reactions can be exothermic or endothermic. Changes of state such as melting ice or boiling water can also be exothermic or endothermic. What is important is determining whether energy, usually in the form of heat, is given off, exothermic, or absorbed, endothermic. So what I added to our notes, when molecules change from solid to liquid, they need more energy. So when they are taking in energy, that makes it endothermic. Therefore, melting as well as boiling is endothermic. The reverse, freezing or condensing, causes molecules to slow down because they have less energy. They release the energy and they are exothermic. And just remember, phase changes are physical, right? Also under exothermic, I'm adding the example of combustion. Hand warmers are another example of exothermic reaction. Some hand warmers consist of a cellulose bag, iron, powder, water, and vermiculite to absorb the water. The water is contained in a thin inner bag surrounded by the vermiculite iron powder mixture. When you break the inner bag, the water and oxygen from the air react with the iron powder and begin to oxidize or rust the iron. Once begun, the reaction below cannot be reversed and the hand warmer must be thrown away. So that's why it's only used once, because it converts the iron and the oxygen into rust and heat. Another type of hand warmer uses liquid sodium acetate encased in a plastic bag with a metal disc. When you press the metal disc, it creates a crystal of sodium acetate. As the liquid sodium acetate becomes solid, the temperature inside rises to the melting point of 54 degrees Celsius. The reaction is exothermic. The bag releases heat energy and warms your hand. This reaction can be reversed by boiling the bag. The sodium acetate will again return to the liquid state and the hand warmer can be reused. Now what about cold packs? Cold packs absorb heat by dissolving salts. Many injuries such as sprains require cold packs to reduce swelling. Cold packs have a thin inner bag of water surrounded by crystals of ammonium nitrate or ammonium chloride. When you break the inner bag, the water dissolves the ammonium salt in one of the following reactions. But either way, look, it says plus heat. So if you notice, the heat in this case is part of the reactant, whereas with the hand warmer, it was given off, so it was part of the product. So you can see by the reaction that the heat was taken in. Both reactions are endothermic. The bag absorbs heat from the surroundings and cools the damaged body tissue. The energy absorbed by ammonium nitrate is more than that absorbed by ammonium chloride, so ammonium nitrate cold packs will get colder than ammonium chloride ones. However, ammonium nitrate packs can explode when overheated, so ammonium chloride cold packs are safer. So I added hand warmers as an example under exothermic and under endothermic cold packs. And remember, they take heat from your skin. So it feels cold because it's taking heat from your body. Heat can only go from areas of hot to cold, or from when it's warmer to colder. You got to be careful about that. Here are some examples of endothermic and exothermic processes. The following processes absorb heat, so they're endothermic, separating ion pairs, changes of state, solid to liquid to gas. These processes can release energy, are exothermic, forming ionic salts, combustion, oxidation, mixing some salts with water, mixing water with concentrated acids, and going the opposite way, changing state from gas to liquid to solid. So go ahead, you can write those in your notes. For any chemical reaction, the total energy in the reaction stays the same. Consider a chemical reaction like the oxidation reaction in the disposable hand warmer. Although the reaction was exothermic, the heat energy did not appear out of the blue. The energy was stored in the bonds of the reactants. So the total energy before the reaction and the total energy after the reaction is the same. This principle is called the law of conservation of energy. It is similar to what you learned about the mass of reactants and products in stoichiometry, the conservation of mass. In fact, the more precise description is that for any chemical reaction, the mass and energy of the products must equal the mass and energy of the reactants. This is called the law of conservation of mass and energy. So my time's going to run out, but hit the pause button and add the rest of this to your note, the law of conservation of energy. And the last slide I put on right here is just the review slide.